Welcome, everybody. So I'm going to be talking to you today about building secure environments in the cloud. So thanks for the introduction. I'm not going to say much more besides the fact that one of the projects that I'm currently working on is with the UK government on a cloud automation project, and a lot about what I'm going to be talking to you today is going to be based on that. So that's my Twitter handle in case you want to tweet about this. So the agenda for today's talk is that we're first going to have a look at what the actual problem is that we're trying to solve, what the options are out there to do this kind of stuff already, and then how we've gone about solving that. And then we're going to conclude. So first up, what is the actual problem that we're trying to solve here? So the cloud market has evolved quite a lot recently. It was previously sort of just only dominated by the likes of Amazon, but now you have people like Google, Azure, and even smaller providers in the sort of OpenStack space. And although many organizations have successfully been able to take advantage of cloud computing, for your more sort of traditional enterprises and organizations, and the governments included, they found this a lot more challenging. With all the sort of different clouds out there, there's fundamentally different offerings, but at the same time, you also have developers doing things one way in Cloud A and completely something different in Cloud B. And from the traditional IT operations perspective, they kind of look at this and they say, I'm not really sure that you're being secure, or how are these environments actually being created in the cloud? I don't think that we can really allow things to go to the cloud if we're unclear about how this is being created. So instead of sort of embracing it, they tend to sort of steer clear. But instead of abandoning it completely, many of these organizations, and the governments included, has realized that they can still reap a lot of the benefits out there, provided they can have a way to create this infrastructure in a way which addresses their needs. And that includes things like making sure it's secure, as well as making sure that it's transparent in terms of how things have been created, and that there's not this perception of just cowboy coders out there arbitrarily creating VMs in the cloud. So when a development team comes along in these organizations, rather than asking for an environment to be created, rather than simply going and spinning a few machines up in their local data center or in a cloud, what we're really after is creating a repeatable, auditable, secure environment in a particular cloud provider. But besides this sort of basic premise, there's also a desire to be able to recreate or move that environment to different cloud providers. And the reasons for this can vary. It can be strategic or financial. It can be technical. Sometimes you have better latency guarantees in one cloud compared to another. Or it can be workload driven. And this is the primary sort of case. So quite often you'll have cases where people are very happy to run their development environments in the public cloud, but then when they have sensitive data, they rather want to run that either in their internal cloud or in a different cloud that will offer those kind of guarantees for them. But whatever the reason, avoiding vendor lock-in is a very popular request nowadays. So in summary, the problem we're trying to solve here is how can we create these secure, repeatable environments in different cloud providers? And particularly from two perspectives. From the developers' perspectives, we want to make this really sort of fast and efficient. At present, it's not unheard of in many of these organizations for their requests for environments to take weeks, if not months, for them to be spun up. But at the same time, we also want to address management's concerns and make sure that the way that we do this means that they can be confident that it is secure and it has had appropriate best practice applied to it. So for the rest of this talk, I'm going to use a concrete example to describe and illustrate my points. So let's assume that you have a team which is going through a process of converting their monolithic application to a microservice-based architecture. The architecture has been set for them. They're going to have a Kubernetes architecture, and maybe the architect is not quite happy with this persistent storage thing yet, so we don't want a containerized database, we want a real Postgres database or something in the infrastructure as well. And that team is now coming and asking for this environment so that they can begin doing their work and doing their development. So as far as this team is concerned, the sort of key functional components of what their environment looks like is that they would like a Kubernetes cluster and they would like a Postgres database as well. But once the fundamentals have been established of what this environment looks like, they just want to go to the system and say, I want one of these environments these are some configuration values. I want 3 Kubernetes slaves, and here's the SSH key I want to be able to log into all of my boxes with. So that's fine, provided you only have one team. But this solution aims to provide a way to create environments for different kinds of people as well. So let's say you have another team that wants to create their Jenkins jobs in a tooling environment. In that case, there are some services which will be common across the environments, things like DNS, and in our particular case also an OpenVPN service. So all of the clouds that we are currently spinning up are completely isolated, and you need to be able to have a VPN in order to get in and actually kind of work in it. So we want these to be present in all of the environments that we spin up. So at the end of the day, what you land up getting is this concept of an environment contract. And this defines exactly what the user can expect to get out of one of these environments when they spin them up. So a self-contained environment with an agreed but a customizable IaaS layout and some base software potentially installed on it. So what are the options out there, particularly if you want to spin infrastructure up in different clouds? So as soon as anybody talks about multiple or hybrid clouds, you are inevitably going to come across what is called the cloud management platforms. And there are various commercial and open source sort of tools out there, but they claim to offer to give you a single pane of glass to do everything. Your IaaS provisioning, your configuration management, monitoring, absolutely everything. And some are better than others, but they all suffer from exactly the same problem, and that is that they try to be all things to all people, and they land up mastering none of them particularly well. They also play in catch-up quite a lot of the time, so if you have a cloud provider that's not supported, it's tough luck. You've just got to wait until they actually support it. And it's quite integrated. So we said, well, rather than going for this one-size cloud management platform solution, why don't we look at trying to find the right tools for the job and bring together the tools that will enable us to achieve the same thing, but in a more flexible and modular approach. So you might say, well, that's fair enough, but you can't arbitrarily just throw a whole bunch of tools together and hope that you're going to get a cohesive solution out at the end. You need to really think about how you're going to go about doing this. And for us, the key to doing this was to have a set of principles which governed both the tools that we chose in each space, as well as the way that we chose to integrate them. And then provided you stick to your principles, you can potentially swap out tools, but you won't completely derail the end goal that you're trying to achieve. So for us, the principles that we followed can be described by an ASAP acronym. The first one is that we want to automate absolutely everything. The goal is to have fast, repeatable environments, and if there's any humans involved, obviously that's just going to go slower, and manual configuration is error-prone. One of the other goals is to have flexible environments, and this is both from the perspective of being able to spin it up in a particular cloud provider and potentially recreate it somewhere else, and also the tools that we choose. We may want to swap tools out. So we very much feel you have to be able to completely separate your configuration code from your config from your code in order to achieve this. And obviously, in order to automate things, you need completely API-driven clouds and tools. And although we certainly don't discount commercial offerings, our preference is really for modular open source tooling. So the two areas I've kind of described the problem can be described in two broad areas. There's the self-service functionality, which is how the developers go and ask for one of these environments and fill in the information about how it can be customized. We're not going to focus on that. We're going to assume all of that is done. Now we're going to kind of look under the covers and see what are the tools and things that we've used in order to actually make this happen. So we have our environment contract. We're now going to give a bit of a high-level overview of the various tools and then delve a bit deeper into each of them. So the first tool that we have is Packer, and we use this in order to ensure that we have consistent base images in all of the different cloud providers that we need to go to. Once we have that, we then use Terraform in order to create the sort of macro-level infrastructure, creating things like the networks and the security groups and the actual VMs themselves, and those are based on the base images that we spin up. We then hook into the VM bootstrapping mechanism on the individual clouds, something through Cloud Init, but ultimately we then just hand off to a configuration management tool of choice, be that Ansible or Puppet, in order to actually convert these vanilla instances into a particular software. And across all of this, we want to make sure that all of the security is handled, and for this we use Vault. So you might look at this and say, well, that's a bit of a it's a mutable infrastructure that you are describing there. You're not baking the software straight into the image. And what you've got to realize is that for a lot of traditional enterprises, they are only starting their journey towards cloud. And this is one of the sort of most common patterns that we see them trying to use to start their journey. There's also a lot of sort of legacy projects that the solution needs to support. So some people will come with a lift and shift type attitude, and sometimes that works and sometimes it doesn't. But what it means is that they may bring with them sort of stateful architectures, and it's a lot harder if you have to completely recreate your base images from scratch. So we do actually support doing immutable infrastructure as well. And in the particular case that we've got here, it's not necessarily that bad, because although we have, for example, Kubernetes being bootstrapped by Puppet, Kubernetes itself would allow you to actually have an immutable application deployment process on top of that. So how have we gone about doing this? Let's dive in a little bit. So I'm not going to go into exactly the same level of detail for all of these, but the first one that we're going to have a look at is the automated image provisioning. And like I said before, we use Packer in order to create our base OS images in the cloud. Different clouds will have different starting points. So for example, if you've got a CentOS 7 image, it's not necessarily guaranteed to be the same image in Amazon as one that you might have in your internal data center or a different cloud. So we use Packer in order to consistently build out the base images and make sure that we have all of the base starting software and all of the security measures that need to be built into that image as a starting point. The next sort of challenge is obviously the sort of automated infrastructure provisioning. And here we're going to dive in a little bit more. So here we need to automatically create the different resources in the clouds. So our environment contract has assumed a certain sort of basic layout, security rules, and VMs. But depending on whether you try and spin this up in Amazon or Azure, the APIs are completely different. And they're completely incompatible. And in fact, there's almost whole features in some clouds that are available and not in others. So the lesson here is really that there's no such thing as a common cloud API. We looked at a few libraries, things like JLib and libcloud, to do some of this stuff. But at the end of the day, all that happened was that they would try and confine you to the lowest common denominator. And we weren't really interested in this. What we wanted was to embrace the fact that there's different clouds with different offerings and have a tool that will do that for us. So obviously, we chose to just smash it all together with bash scripts. No. This is HashiCorp conference, so obviously we used Terraform. So many of you are probably using Terraform already, so I'm not necessarily going to go through the basics. Rather, I'm going to tell you about some areas where it was a key selling point for us in terms of solving the problem that I've just described. So the first thing is that it obviously supports all the major providers out there. And this means that we can apply the same paradigm and the same sort of approach in order to building the infrastructure. We didn't need to resort to things like CloudFormation for Amazon or Heat for OpenStack. But the fact that there's a pluggable provider API was key for us when we ran into our first cloud that wasn't actually supported. So because of this, we thought, well, we now need to actually create a provider ourselves. And because the tool itself has an API, which is one of our requirements, we landed up actually writing the VMware vCloud provider, the provider, and contributing that back to HashiCorp. So that allowed us to basically bring on board a cloud, which if we'd gone with a cloud management platform, just wouldn't have even been possible. Here we have an example of, in our case, I told you that we have an OpenVPN box. And we have the instance at the top and a subnet at the bottom. And this is the way that we would declare this in an Amazon setup. Obviously, it's going to be completely different in OpenStack. In this case, we have a compute instance with a floating IP. And here you'd need to take the floating IP and essentially assign that to the compute instance in order to make that available out on the internet. But at the end of the day, regardless of whether we build it this way in OpenStack or using the Amazon setup, we achieve the same end result. So you may have noticed that there's a lot of variables in the example that I've given you here. And this is also very key to us. So the way we've structured all of our Terraform setup, we need to be able to essentially dynamically generate our Terraform setup and also pass in configuration. And that's both from the user. So the user will have said, I want 3 Kubernetes nodes, but we also generate some information to ensure that we create these environments in a consistent manner. And it's this basic support, along with the fact that Terraform allows you to link your resources or link the output from one resource into another, that provided us with the basis for being able to generate a setup that allowed us to actually do this. So you can see here how we've got our floating IP defined for OpenStack, and that's being used as input into our OpenVPN instance to ensure that it's exposed out onto the internet for us. So behind the scenes, in order to make this possible, we've made heavy use of modules. And our modules are broken down. Some of them are quite granular, and some of them are quite maybe a little bit more less granular. But at the end of the day, we have a very clear sort of requirement to have a consistent way of defining our inputs so that we know what a module is allowed to take in, and also the outputs that will come from that. So here is a simple sort of DNS module, but it's an example of how we do that. So modules are your friend, and in terms of the Kubernetes setup that I've described, this is sort of what it's going to look like when we start combining these different modules. So here we have an example of a management module, which is there to control the management aspect of our environment that we're spinning up, which allows us to have the OpenVPN server and make that available. At the same time, we have a different module, which is the DNS module, and then we basically try and hook those two together with the clear definitions that I spoke about, with these are the outputs that are going to come from, in this case, the management network. We expose the OpenVPN IP, and then we can use that as input into the module which is defined to provide us with our external DNS. So this will allow the people to actually go to the correct OpenVPN DNS entry in order to get into their clouds. So even though when we started out on this journey, we thought we're only going to be spinning infrastructure up in one cloud provider, and then we will move the whole thing somewhere else. But quite quickly, we came to the point where we actually needed to combine infrastructure from different cloud providers. And the DNS is the example here. So luckily for us, Terraform provides a way to hook into things that are not just compute resources, but also DNS providers and PaaSes and other things as well. So where we were using Amazon Route 53, if we spun our infrastructure up in Amazon, everything was contained in one cloud. But if we chose to spin it up in an OpenStack setup, then suddenly we're spanning multiple cloud providers. And the fact that Terraform allows you to do this was one of the key selling points for us, because we need to both be able to create infrastructure in different clouds, but actually combine them together as well. And there aren't really any other tools out there that do this particularly well. So just going back to our example, this is the setup for an OpenStack-based cloud, but you can see that we've actually combined the infrastructure from an Amazon DNS entry and an OpenStack cloud. So the summary for this particular section is that in Terraform, we've very much found a tool that adheres to our ASAP principles. It's completely automated. We've managed to separate out our configuration from our code. We have an API-driven tool, and our preference for a modular open source tool has been adhered to. The key selling point, simultaneously be able to combine different infrastructure, and as I said, we actually compose and generate our Terraform definitions. Terraform itself has, for us, some limitations in terms of things like being able to loop over entries, and this is functionality that we needed. So we've essentially written a layer which sits in front of that and goes through the process of looping through things and then generating some of the content that you saw over there. So that's how we get around that particular piece. And the fact that we have infrastructure as code is now essentially something that the management side of things was really worried about. The fact that they didn't have a clear understanding of how infrastructure was created in the different cloud providers can now be addressed by the fact that they can go there, see exactly how it's set up and it's auditable, etc. So, on to the next challenge, which is how we go about automating the instance management. So, we've tied everything together at a macro level. Let's dive into the boxes. So there's two aspects to this problem. There's how do we do it the first time round, and then how we do the maintenance sort of going forward. And the key lesson for us here was that we made a very conscious decision to decouple the initial bootstrapping mechanism from the ultimate configuration management tool that we chose to use. Specifically, we only want to be able to do very minimal bootstrapping with our initial bootstrap mechanism, which is Cloud Init, and then just hand over to a configuration management tool of choice. So I'm not going to talk about the particular configuration management tools. There are many out there, and there's many wars as to which one is the best one. Take your pick. In our particular case, we happen to use Puppet. So let's focus on how all of these things fit together in our broader solution. So for the moment, if you just ignore the piece on the left, we're going to come back to that. This is where Terraform left us. So we have our infrastructure, which has been created. We have all of the networks, the security groups. Thanks to Packer, we've got Cloud Init installed on our base images, and we have a consistent starting point in any cloud provider that we start up in. For those of you who are not aware of what Cloud Init software is, it essentially allows us to do boot time customization on the instance. It's open source and it works across the cloud providers that we support, so it ticks a lot of boxes for us. And the way that it works is that it hooks into the cloud provider's metadata service. So when an instance comes up, it can register and say, oh, well, this is the sort of host address, and you can then programmatically get hold of that information and use that as part of your bootstrapping. But the most important thing for us is that we need to inject some custom user data that will allow us to configure the bootstrap mechanism going forward once the box comes up. So Cloud Init allows you to do configuration either through shell scripts or YAML. In this case, we've got an example of being able to sort of set the host name. But for us, the important thing is that we really just want to bootstrap the configuration management tool and allow that to then take over moving forward. So how do we actually get this information into the metadata service in the first place? So we know that Terraform is our tool of choice to be able to do the infrastructure provisioning, and it allows you to do things like define a template to do this. Now I know that actually there's the template Cloud Init config, which is a more recent resource which has been made available, but for the moment we haven't actually changed some of our setup to do this. But what it essentially allows us to do is, through all of the configuration that we've received from the user and our generated content, we can generate a Cloud Init config that's tailorized to the particular image that we're booting up and allow it to be bootstrapped. And that then just gets passed in through the user data when we actually create the individual machine. So we basically got to the point where we've booted up and the Cloud Init process is run and it's triggered our automatic scripts. In our particular setup, if we think about our Kubernetes example, we have a designated orchestration box in our setup, which is the big box over here. And that's going to run things like DNS for us. It's also going to act as an internal puppet master so that we can completely bootstrap the cloud from the inside. So its Cloud Init process will go something like this. It will take a token, which we're going to talk about how it gets, and will access Vault. That will allow it to then get the credentials to connect to our Git server, which will allow it to essentially download our Puppet code and then run that in order to convert the orchestration box into a Puppet master and also provide DNS services. The rest of the boxes will wait until the DNS service is ready and then obtain their own DNS entry, and it will also then connect to the Puppet master and ask for it to run a Puppet run on itself, and that will then land up installing all of the software on the individual boxes and turn our environment into a concrete version of the environment contract that was defined. So in this instance, we've got, at least from the bootstrapping principle for VMs, we've got a completely decoupled and asynchronous bootstrap process. So what I mean by that is there's no explicit need, once Terraform has actually run, to kick off a particular configuration management tool. It simply happens as the environment comes up, everything starts self-bootstrapping and aligning itself. In the same way that with Terraform, we had infrastructure as code. In our in our Puppet setup, we have a similar setup. And that means that, again, one of the concerns by the sort of traditional IT operations people was that we can't see what you're doing. We don't understand how these environments have been set up. And again, it's now completely sort of transparent to them. We've adhered to all of our principles, so we've ticked all of the boxes there. And one of the things that we found was that we had one of our environments where we actually started off with an Ansible with an Ansible configuration management setup, and the client wanted to move to Puppet. And although this wasn't a completely seamless experience, there were some issues involved, it was self-contained to the area that we were operating in. So we didn't have to worry about the fact that we were going to destroy networks or the fact that we needed to change that aspect, because that was managed by Terraform. So on to the final area, which is how we go about securing all of these things. So security is a big topic, and obviously we're not going to be able to cover everything, but we know, at least from Terraform's perspective, we've managed to have the fact where we can define things like security groups, network setups. So from a perimeter boundaries perspective, we have that angle covered. We also ourselves run a PKI infrastructure ourselves, where we generate certs and assign them to the boxes, and that we're also going to be moving to use Vault in the future. But the area which cuts across all of the tools that I've spoken about thus far is secrets management. And this is in terms of, it crops up everywhere. How do we get the secrets when we want to actually provision the environment in the first place into Terraform? Once we have our actual environments bootstrapping, how do we get the database passwords and things like that into the environment to move forward? So we wanted a consistent way of dealing with this across all of the tools that we were using. So again, one of the sort of key concerns for sort of management is that especially if you have developers doing one thing one way in the security context, they really worry about that. So if you can offload all of the security-related work to a tool which is dedicated to doing that, it's a much easier way for them to be able to audit it and understand that it is doing sort of best practice. So the lesson here is basically don't roll your own. Unless you seriously know what you're doing, rather use a tool that understands and is dedicated to doing this for you. And obviously the tool here for us was Vault. And to be honest, we haven't really found anything else out there at the moment that has given us the kind of flexibility that we can get from Vault. So obviously Vault's sort of goal is to be the single place where you can go to do secure secrets management through a tightly controlled API. And for us, it's not just the fact that it's a backend that can store secrets for us. The fact that it has policies means that we can create our secrets in particular areas within Vault and then only allow certain parts of our tool set to have access to it and certain people to only have access. And this is very important to make sure that we can comply with various policies. There's audit logs as well, so in the event of a sort of compromise or whatever, you can actually also be able to see what's happened, etc. So these are all the things which make it a fantastic tool for our particular problem set. So in our particular setup, we run a centralized HA Vault, and that's backed by a console database. And we then configure all of our tools and processes to be able to talk to that. We could have had each tool do this itself. So for example, Puppet's got encrypted Hera, Chef's got encrypted data bags. But if we did that, we would just land up with a secret sprawl all over the show. Like I say, we really wanted to make sure that we had a single way of dealing with all secrets across the solution. The integration efforts with the individual tools vary. So we're making use of an existing Ruby gem for Puppet, which we'll talk a little bit about. But unfortunately for us, things like Terraform doesn't actually have native integration with Vault, something which I'm told will hopefully be coming relatively soon, but we'll see. So we're looking forward to that. But one of our key principles was that any tool that we choose needs to have an API, so that if we get to the point where we find a setup where there isn't any integration, we can write it ourselves. And that's exactly what we needed to do for our particular setup. So let's have a look at how we do the infrastructure provisioning process. So although I said that absolutely everything is automated, there is a one-off manual process where we need Vault to be initialized and to be unsealed through a variety of different people. But once this has been done, it's then available for our environments and our various tools to be able to interact with. Although you'd hope there's no sort of global sort of static secrets, in reality that is the case. So there will be certain human intervention where people will be able to configure those kinds of things. But as we'll see moving forward, we also generate secrets as well. So this is just an example for those of you who may not have come across Vault. So here we are writing a fictitious cloud provider password into Vault and then just reading it out again. None of the stuff here is real data, obviously. So in our particular setup, we have our development teams, and they're going to go and request one of these environments. And the process will go something as follows. They'll create a new environment or request for it to be created. They'll fill in a few details. So in our example, they'll say, I want my conversion Kubernetes environment, give me my 3 nodes, and here's my SSH key. The broker will then kick off a process where, as part of what it does, it will go into Vault and it will create a specific mount point. And this is where it's going to generate all of the secrets and or copy secrets into to allow for the bootstrapping mechanism for that environment to move forward. So once that foundation's in place, our developers are then able to simply go to the system and say, spin the environment up, do what they need to do. They can completely deprovision it as well. And it allows them to do this numerous times, basically. So when they ask for their environment to be spun up, what will happen is that the brokering software will understand the target cloud infrastructure that this environment has been spun up in. It will go to Vault, and it will obtain the secret that it needs, and then it will write that into a TF-vars file for us and make that available for Terraform to do the actual provisioning. So this is the place where there was no native integration to Vault for us, and we wrote, as part of the sort of software that we wrote a Go client to be able to interact with it and get the secrets that we need, and then essentially generate a TF-vars file for us. Now, as many as you will know, there's always state that's involved when you're working with Terraform. And for us, there's the possibility that some of the data that will be passed into Terraform will be secrets. And we need to ensure that obviously this is not going to be exposed anywhere. So we encrypt our TF state file, and we have a little utility that we wrote called TerraHelp that does this. It has the ability to just do sort of standard encryption, but one of the things that we got it to do was essentially take advantage of Vault's transit backend. So this allows you to do encryption as a service. So essentially what we do is we'll take our state, we'll send it off to Vault, we'll ask Vault to encrypt it, we'll get the encrypted value back, and then we ultimately store that in our data store at the back. So the benefits for us here is that we have a complete sort of centralized secure storage solution. All of our infrastructure provider, passwords, configuration, in order to connect to them that's sensitive, is all defined in one place. We also have flexible backends. So we make use of the generic backend, but as I've described to you as well, we're also taking advantage of Vault's transit backend. And the fact that we can do this means that for different aspects of the security solution, we can choose the right security for the job, essentially. So take advantage of whatever makes best sense. So some providers are going to be able to do more sort of fancy things. So things like Amazon, there is a backend in Vault that allows you to dynamically generate your passwords, something that we're moving towards. But other providers are not as sort of flexible, and they say you have to configure a static setup, and that's it. But this will allow us to take the security to the highest level that we can for the individual cloud providers, whilst dealing with the situations where cloud providers don't allow that to happen. So the final bit is how do we go about securing the automated VM bootstrap process. So in the previous section, I said somehow magically that we managed to get a Vault token into our orchestration box, and that was used in order to connect to Vault and move forward. So now we're going to have a look at how we did that. So this is where we left off, but you didn't quite get the full story in this picture. So essentially what happens is that when somebody creates a new environment, as I said before, we will create a specific mount in Vault. We will also generate a dynamic policy that will make sure that the secrets that we've just generated are only going to be able to be read by a bootstrap process in Cloud Init and Puppet on the other side. Here we have an example of, this is manually how it would be done. Obviously we're doing it through an API. But it's the equivalent of creating a mount point here for team 1. And if you list the mounts, you'll be able to see it. We then have the secrets written into it. So in this case, it's a fictitious Git password, as well as a Postgres password, potentially. And we also will have generated a policy, which says that when we create a token, the only thing that you're going to be able to do is be able to see the secrets for team 1's environment, not any other environment that may have been created. And we use that policy essentially to create the token that we ultimately want to pass over to the Cloud Init process. Our mechanism for getting the token there, however, is Cloud Init. And as some of you may be aware, Cloud Init is not necessarily secure, because you can go onto the box, and if you actually have a look at the Cloud Init logs, you'll be able to see the token in clear text. So we needed a way to be able to somehow securely get this token onto the box. And we leveraged Vault's cubbyhole backend to be able to do this. So the way that we do this is that we generate 2 tokens. We generate the real token, which is based off that policy, and then we generate a limited time token as well. We take the real token and we store that in a cubbyhole backend. And we secure that against our limited use token. And it's that limited use token that we then embed into the user data and pass that through to Cloud Init. So once it arrives on the other side, we land up with our box, which has got our limited use token available for us to use. We can then take that and use that in order to gain access to the cubbyhole area. And this is the only thing that that token is able to get hold of. That allows us then to retrieve the real token, which we actually embedded in the cubbyhole in the first place, and then use that moving forward. So I was really happy to hear from Mitchell that the resource functionality in Vault is coming along, because that's something that will make this process actually a lot easier for us to deal with. So when you actually retrieve the token, in our particular case, the cubbyhole will be destroyed. And that's just the nature of how Vault has been set up with the cubbyhole. So that token said, I only have 1 usage by the time I get to Cloud Init, and the act of actually using it meant that it was no longer in use, the cubbyhole got destroyed, and we essentially just land up with our real token on the other side, although we've never actually passed that in any sort of clear text into the VM in the first place. This is not a perfect process. There are certainly windows for, if your Cloud Init fails, you potentially have a token lying around that's not being used yet, which has access to the credentials. But again, we've kind of tried to use the policies to ensure that we scope it to only being able to use what is required in order to do this bootstrap process. You need to kind of mitigate that by sort of auditing and watching things. And it's something that we're still working on and experimenting in this particular area. So, just moving forward, that real token is then we connect into Vault. We can then gain access to all of the credentials which we wrote in there. As I said before, that particular token has been scoped to only allow access for the team that we spun the environment up for, which then, as we saw before, can connect to our Git repository, download it, and initiate a Puppet run on us and convert our software. The particular integration that we use for Puppet is a Ruby gem called Hero Vault. And in our particular case, the way that this works is that every time you do a Puppet run, it will go to Vault and request the various secrets, make it available, and then allow it to be configured. So, for example, if we needed to configure things like the database password for our Postgres database, it would go and retrieve that, and then we would be able to set that up. It's currently only works with a generic backend, however, so we're working on changing that so that we can take advantage of, for example, the dynamic Postgres functionality that we might want to be able to use in a scenario like this. So our secrets management, in Vault, we've really found a tool which embodies our ASAP principles. We have a secure storage solution, and we have flexible backends so that we can choose the right tool for the job. The granular access control means that we can restrict what gets created where. So, in conclusion, we've looked at a lot of different technologies as part of this whole solution. But if we go back to what the original goal was, we want to be able to create these sort of fast, repeatable environments capable of running in different cloud providers. And we said we want to do that from two perspectives, the development as well as the people who are a bit unsure about how these environments are created, and give them a little bit more confidence that this is a secure way of taking advantage of things. So we got to the point where we have our developers which are now able to spin up and down environments in minutes. Like I said before, this could take weeks or months for some of them to actually request an environment. Now, if they want a test environment, they can go there, they can ask for it, they can spin it up, destroy it, and this can happen as often as they choose. We've addressed some of the concerns that people had before about no visibility into how the infrastructure is actually being created in the different cloud providers. We've addressed their security concerns as well. And essentially what it means is that they can start leveraging the promises that they've been told about cloud. So as I said to you before, they're still on a journey towards moving to cloud, but this really allows them to be able to take their first steps in that place. And most importantly for us, you can actually choose the right cloud for the job. So if you have particular requirements that it must run in a certain cloud, you can spin your environment up there. So rather than using a single one-size-fits-all tool, we've combined a lot of different tools together, and we believe that that allows us to be flexible and adaptive moving forward. So the cloud is changing constantly, so are the tools, so are the options. So if you want to be able to take advantage of these various things, we very much believe you need to try and bring together a modular set of tools in order to make this happen. So basically, be true to your principles, but be flexible in the tools that you choose and your approach, and that way you have a better fighting chance of being able to take advantage of things in the future. Thank you very much.